Okay, only for this class I have to since open the comments in these two places. So only for the first class it is there. All right. Okay. All right. Okay. So let us begin. Okay, I can see your chats here. Good morning, Prudvi, Vaishnavi, Dhanush. Okay. Shubham. All right. So let us study magnetism. Okay, please have a look at this slide which is in front of you. As you can see here, first of all, we see that there are two magnets. We will go into the details. This is just for the summary slide, what all we are going to study. So first of all, you can see here that there is a magnet, yes, and the north pole of one magnet is facing in this diagram. If it is facing the north pole of another, will it attract? Will it show any kind of, say, attraction, or will it show repulsion? Most of the times you see that magnets are drawn with the, say, attraction one. But see, if the north pole is towards the north pole of a diagram, or in the magnet, if the north pole is towards the north pole, in that case it will show repulsion. Okay, and if the north pole is towards the south pole, it will show the attraction. We will learn more about this, but as of now, if you are using any electric appliance, if you are using any, say, anything that has a charger attached to it, if you will take a coin near to the charger, whatever you are charging, like this laptop charger, you will feel that there is something which is pulling the charger and the coin near it. Now, none of these are magnets, but still you will see such kind of a thing. So wherever there is electricity also, even in case of, forget about the higher level conductors, but even in case of your simple charger also, if you will take a coin near, you will get that feeling. Okay, some kind of attraction is happening here. So electricity also creates magnetism. It is not only by the magnets which is creating this attraction or this repulsion. Now, just a quick recap of what we studied in motion. If you will try to remember, then in motion you had studied, okay, every action has an equal and opposite reaction. Remember? That was in motion. Now, in physics, though the topics are different, though the concepts are different, but even in case of magnetism also, there is not that one which you studied in motion, but here is also some kind of force is here and some kind of attraction and repulsion is here also. Okay. So in electricity, if anything that has electricity passing through it, you will see that there is magnetism. And in 1820, Hans Oersted, he discovered that electric current creates a magnetic field. Okay, electric current creates a magnetic field. Magnetism was there in our class 6th NCERT as well, which is available on the YouTube channel, right? So if you will see, then there also we studied magnetism, but it was in a very simple terms. Like in ancient times, when the sailors used to sail through their ships, in that ships, how they used to find the direction? Was it only by the help of the winds, by the stars, by the compass, or say they also had some kind of stone which able to guide them? Even before the compass, how they were able to find the direction? What is it that they used? So that we had covered. That is a part of class 6th NCERT. Okay, you can go and check that. Now, in case of around 600 BC itself, there was the word magnet which comes from the word magnesia. Now, this magnesia, or this use of this, say, stones, which I told you for the ships also, what they used to use even before compass? This, they used to use this lodestone. This is there in class 6th NCERT. Lodestone. These lodestones were able to guide them in the sea. Okay, and the use of the lodestone you will find in 600 BC times also, when sailors were sailing even before the compasses. At present, if you will see, then we use the word magnet. At present, we have the compass. So where do you trace the origin of this word? This word comes from the word magnesia, which, you know, in Greece, it has the origin in Greece. Okay, and there lodestones were also used. Now, coming to the power of electromagnetism, as you must have seen by now that if a wire is carrying electricity, if you are taking a coin near to that wire, then it will show some kind of, say, attraction to that wire, right? You must have already seen this. So what does it means? It means that wherever there is electricity, and that electricity has created the magnetism. So let me combine both of them and let me call it as electromagnets. Okay, let us call it as electromagnets. Obviously they are temporary, because if you will withdraw the reason, if you will withdraw the electricity, right, in that case what will happen? The magnetism property will also be removed. And the most simple rule with which we are going to start now is that the rule of the poles: opposite poles attract, North Pole and South Pole will attract, opposite poles attract, and like poles will repel. That is, if a magnet, you are cutting it into how many pieces, how many small pieces, it doesn't matter. Every small piece, the smallest piece of the magnet will also have, even if you are cutting it this small, this will also have a North Pole and South Pole. It is not possible to separate it completely. Okay, so doesn't matter how small you are cutting it, doesn't matter how big it is, irrespective of the size of the magnet, there will always be a North Pole and always be a South Pole, and always the North Pole and the South Pole being opposite will attract, and the North Pole being the same and the South Pole being the same, they will repel. Okay, now coming to the use or the application of the big electromagnets, how they are used? They can be used in the cranes for lifting. With the help of a magnet, they can pick this up. This can be used in case of, say, separation of the metal from the non-metal from any dump yard. Then electric bells, the property of magnetism is used. For motors it is used, speakers it is used, and even for the purpose of data storage. So for all of this we see the use of magnetism. Okay, so now if we have understood this, that means we are good to go. And even this summary also, if you will revise, then also you will have some kind of an understanding at least. Okay, so coming to this invisible force, one, if you are punching another person, that is a visible force. It will be quite visible in the other person and as well as maybe in this person also. But if you talk about magnetism, it is the invisible force. You will not see it directly, right? But you will see its actions, right? A comprehensive principle, law, and electromagnetic applications. That is what we are going to see. So take any piece of magnet, if you will bring some, say, iron nails near to it, if you will bring some iron nails near to it, a bunch of, say, small iron pieces or small iron nails, you will observe that these nails will be attached more to this and these nails will be attached more to this end. To both the ends it will be completely attached, and in this middle region this attachment will be comparatively less. They will try to pile up around this part. So what has happened? Why they are either putting up to this corner or to the South Pole corner, but not in the center? Here it will be very less, right? So why it is happening? If you will draw this into, if you'll picturize this in that NCERT one also the diagram is there. If you'll picturize this or if you'll draw it, since in this class we want to go a little bit, you know, deeper than that. So if you will draw this into the lines, then you will observe that they will have the more intensity in the north side or in the south side compared to this particular region. Okay, so that is how you can draw the lines and understand, okay, whatever force this is, it is more in this ends, towards this ends, right? What is the definition? A physical phenomena where materials exert attractive or repulsive forces on other materials. Okay, just like in case of gravitation we had seen that, okay, every object is attracting every other object. Here also that is, and again, another topic, but it was so easy to imagine that, okay, everything is attracting everything. So here also those who will have the property of magnetism, say cobalt, nickel, iron, any of these, combination of this, all of this, they will show the phenomena of, say, attraction or repulsion on the other material. Okay, like not everybody had that electricity property. Similarly, not everybody will have the magnetism property, right? So if those materials or those phenomena where these materials are doing the attraction or the repulsion force where they're exerting, then we can call it as, okay, they have the magnetism. Now, in ancient times, for the navigation, they used to use the lodestones. They used to use the lodestone. If you will see, they have a combination of iron and, that is iron oxide, Fe3O4, the iron, the composition. And now also you know that iron, nickel and cobalt, they will show the magnetism property. So even though they did not have the compass as such like we have in present times, but still they were able to use it. Now what is the origin? The origin is from magnesia to magnetite. And what is magnetite? From here you are able to extract the iron, and that time you are able to extract the lodestones. From there you used to get it. Okay, so magnetic ore deposits are found naturally in the earth. It is just like the iron ore deposits, hematite, magnetite, etc. So like that, the magnetic ore deposits also, you were able to find it. Okay, where this name came from, this name, say magnetite, or this name, it has the origin in the name Magnesia. And what was Magnesia? Magnesia was an island in Greece. Okay, and natural magnets, all the natural magnets are permanent magnets. If you are making a magnet into a permanent magnet with the help of electricity, if they're electromagnet, then if you will withdraw the electric force, that will also be gone. Okay, but natural magnets, they are permanent, but you can see most of the times they are weak magnets. Electromagnets, by determining how much coiling you want to do, the core material that you want to use, you can increase the strength. Okay, and artificial magnets can also be made. Okay, and you can make them stronger because you are the person who is making it. What all are used? Iron, cobalt and nickel are used. Okay, let me just change this to, okay, coming to this. Now coming to a bar magnet. What is a bar magnet? It is based on the shape of the magnet. We are calling it as a bar magnet. Okay, in the end we will try to do 25 questions, so just I have to move at a faster pace because we want to do at least 10 questions. Okay, rest I'll give you the PDF. Okay, now coming to the bar magnets, it is just the shape. There can be bar magnets. You must have heard about the horseshoe magnets. It is the horseshoe shape that is attached to the feet of the horse, right? So that is there. Similarly, there can be different shapes. Okay, if there, what is the property? If they're freely suspended, they will always align in the north-south direction. If they are freely suspended, they will align in the north-south direction. All right, and doesn't matter how much you are cutting, doesn't matter how much you are breaking, it will always have a north pole and a south pole. Okay, and what is the law? The like poles will repel and the unlike poles will attract. Coming to the mapping, if I will bring the nails or iron scraps near, and if I will do this experiment, I will see here it will attach and here it will attach. So I can say that how it is happening. Outside I can see clearly that there are, say, loops, continuous loops which are going like this. And what happens inside the magnet? Inside the magnet, you can see that from south to north, they can move in this kind of a way. Okay, now these directions, they are not able to ask in the exams. So just a second, I will come to window capture. Some of the pictures are going away here, no? That's why let me just change this to Microsoft Edge. Okay, I think here it will be better. All right. Okay, hopefully it is more clear in this one. All right. Okay, so this we can term it as the field density. What do you mean by field density? It means closer line, if you will observe, it will have the strong magnetic field. That means here there will be the strong magnetic field, and in these regions there will be the weak magnetic field. But how to put it in a better way? So if you want to quantify that, strong means how much strong, how do you quantify it? You can quantify this as in terms of units, what is the unit, and in terms of, say, we can quantify it in terms of Tesla and in terms of Weber. In terms of what? In terms of Tesla and in terms of Weber. Okay. So what are the units? The units are Tesla and Weber. Okay. If you want to find out the magnetic field strength, what is the FBI? Remember Fleming's left hand thumb rule. If you want to find out the strength of the magnetic field, in that case it will be denoted as Tesla. How do you find out? It is 1 Newton per ampere meter. 1 Newton per ampere meter. And the secondary definition, it is another, say, unit. It is your Weber per meter square. Or you simply remember the unit. This is what they're asking most of the times. It is Tesla for the magnetic field strength. Now, if they're asking you about the total number of field lines passing through an area, we had seen there were many lines which were passing through the northern side and through the south pole, right? In the north pole and south pole, more lines were there. But what do you mean by this? That more iron nails are getting attracted to the north pole side and the south pole side. How to put it in a better way? So we call it as the magnetic flux. What do we call it? We call it as the magnetic flux. What does it mean? The total number of field lines passing through an area, it is your magnetic flux. It is denoted by phi. Okay. And if you come to the SI unit, it is your Weber. And how to find out the value of phi? It is the magnetic field strength which you got, the magnetic field strength, and the area which is considered, and cos theta. Okay. So you remember Fs cos theta? On similar lines, you can remember that if you are talking about the magnetic flux, it is, what are you considering here? You are considering the magnetic field. So you take the value of the magnetic field, area upon which it is being applied. So you consider the area and you consider the cos theta. And here theta is the angle of penetration. Okay. Now only they are asking you the units most of the times. Rest of it is not seen in your exams that much. Okay. It is not seen as such. Now coming to the Gauss's law for magnetism. What does this Gauss law says? The law says that the net magnetic flux, just before some time we had seen about the magnetic flux. So what does it, that is about the field lines, right? So what does Gauss law says that the net magnetic flux through any closed surface is zero. That the net magnetic flux through any closed surface is zero. But what does it mean? It means that every field line that enters must leave, right? If we are drawing this field line like this, that towards the north pole it is going like this, and towards the south pole it is going like this, and inside the magnet you can take it in this way. So if it is going like this, then, and if there is a closed, say, scenario is there's a closed surface, then in that case, if you are considering that if a magnetic field line has entered, it must leave. There is no isolated magnetic pole or monopoles in nature. Always there will be a north pole and a south pole, and that is why, as you had seen here, okay, always there, please ignore this, say, this one. So if there is a north pole and a south pole, then always if they will enter, they have to exit. It simply means in the simplest term, we can put it as, see, if there is a north pole, then there has to be a south pole. Individually, they cannot exist. So the magnetic field line, if they're entering, that means they have to leave also. Okay, as simple as that. They have put it in terms of a law. Okay, now come to the discovery of Oersted. Oersted, he had made that discovery in 1820. We had seen in the beginning summary slide also. It is the link between the electricity and magnetism. What is this link? If you are using a current carrying wire, then it deflects a magnetic compass. You want to do this experiment? If you are charging your laptop, you take a coin near to your charger. You will feel this instantly that, okay, some kind of this attraction is there. It can be very minute, but you observe very nicely, you will see. If you want to actually see it, then use a compass. If you will bring the compass near, the compass will show the deflection, right? So electric current produces a magnetic field. This was observed, okay? And it is based on what? How much current it is carrying? Yes, it will be based on that, how much current it is carrying, and it will be also based on the distance. And just like any force, if you will increase the distance, the force will decrease. Yes or no? So here also it is inversely proportional to the distance, and it is directly proportional to the current. As a result of which, by using this current, you can always have strong magnets. So strong, the ones which will not naturally occur, that also you are able to make with the help of this. Okay. Coming to the solenoid, there are always questions for solenoid. So what is a solenoid? It is a coil of many circular turns of insulated copper wire. Okay, copper, you know, is the, say, good conductor of electricity. So copper coil is wrapped in a cylindrical shape. As you can see in this one, it is this copper coils. These are the copper coils you can see, and it is wrapped in a cylindrical shape. Okay, used to magnetize materials like soft iron. And this can be, what is the purpose? It can use to magnetize the material. Now in this case, the solenoid, this copper coils, they will produce the uniform magnetic field inside. Why? Distance is from the current carrying wire, you can say, or from the electric wire that you are considering, from where you want to see this magnetic strength. Okay, distance from that. Okay, if you want to check from this solenoid, say, then at what distance you are keeping from this solenoid. If you will bring it near to the solenoid, it will show, say, better magnetism, and if you are taking it away, it will show less magnetism. Okay, the coil in many circular turns, and it will generate the uniform magnetic field. How it will generate uniform magnetic field? Because the coil is, say, uniformly wrapped, as a result of which it will produce the uniform magnetic field. But if you will see outside it will show the non-uniform field. Why? Because we have seen from the beginning itself, towards the North Pole and towards the South Pole, the magnetism, or you can say, better use the term, magnetic flux will be more, right? BA cos theta will be more, but in this particular region it will be less. Okay, so that is about solenoid. Now coming to, you will get such simple question that which of the following is used in a solenoid. So whenever they're going into little bit detail, the question will become simple. Whenever they're asking very simple question, the question might get difficult. Okay, so take care, observe that pattern. The electromagnet, magnetism that is produced or that is done by using the electricity. Okay, soft iron core is inside a solenoid. If you are using this is the copper coil, as you can see in this diagram. This one is the copper coil where I have marked number 1. Okay, that is the copper coil. Number 2, you can see this is the soft iron core which is being used inside the solenoid. And now how it is working? It is working like a temporary magnet. Field exists only when the current flows. If the current is flowing, then the magnetic field will exist like this. And if the current is not flowing, then it will stop being, or it will stop acting like a, say, magnet at that point. Okay, it can be used with the high, you can see it is directly proportional to the current. So if you are using a high current and you are using the required material, then you will see that in the industrial power they can lift up to 20,000 kg of iron scrap. 20,000 kg of iron scrap can be lifted. So they can lift the cars also, if you have seen in the movies. So it can be that powerful. Okay, now to increase the strength, what to do? You have to increase the current. The more current that you will provide, you will see, if you will coil the charger, if you will do the experiment, then you will clearly observe that if you are putting coils and then you are trying, it is, say, increase the current. And if you are increasing the number of turns, then also you will see that by increasing the number of turns also it will increase. Okay, now coming to the classifications. You must have heard about ferromagnetic, paramagnetic and diamagnetic. Just remember one thing, ferro means iron. Doesn't matter whatever you study, people will tend to forget this. So you remember one word, that is iron. Now attached iron to your magnet. Now iron magnet, that means there will be the strong force of attraction. So by that you remember that ferromagnetic means strongly attracted. End of story. Only this one word you remember. What? Ferro iron, right? So ferromagnetic means it will be strongly attracted. What are the examples? Iron, nickel, cobalt, etc. And they are used for making the permanent magnets. Coming to the paramagnetic, paramedical, paramagnetic, the name itself is telling you that they are weakly attracted. Right? Examples, aluminium, platinum, these materials will be weakly attracted. Iron will be strongly attracted. Diamagnetic, they are so they are weakly not attracted but repelled, weakly repelled, like water, air, copper, they will be weakly repelled. And what is Curie temperature? You must have heard about Marie Curie. What is Curie temperature? The specific temperature at which a magnetic material loses its property, because heat destroys magnetism. That is why there are some magnet care tips as well which are available. And in the magnet care tips we see that you should not heat up a magnet. You should store it with a wood, say, piece in between the magnets. All these things are also there. Okay, so as a result of which, if a magnet is heated up to a certain temperature, at a certain temperature, it will lose its properties. So does heat destroy magnetism? If you will not study this, then you will tick that no, it does not destroy. But what is your answer? Yes, heat destroys magnetism. Okay, at a certain temperature at least it will. So does it matters, or is it independent? So answer is yes, it does matters. What is the right hand thumb rule? Right hand thumb rule is very simple. If you are grabbing or holding a current carrying wire like this, okay, say if I have a current carrying wire, any wire, if I am holding a current carrying wire like this, okay, then in that case, this current carrying wire and the magnetic field, it has the relation. If I'm holding it like this, and if the direction of magnetic field is in this direction, then my thumb will give the direction of the current. Okay, if I hold it in the opposite way, if the like this, if the magnetic field direction is there, then the current carrying will be in this direction. Okay, so it is, if you are holding it, then the direction of the thumb will give you the direction of the current. Okay, and the direction of these fingers and how you are rotating with the right hand, that will give you the magnetic field direction. Those who have studied class 11th science, in that case there were very much details in these topics, and too many numericals were also there. Here we don't need all these things. We simply need that, okay, these are about the Fleming's right hand thumb rule, and these are about the Fleming's left hand thumb rule. Now just like a pistol, just like a, what do you call it, like case of solenoid, direction of magnetic field. Okay, so in case of your Fleming's left hand thumb rule, if just like a, here you have CBI, US you have FBI. So if you will write down F here, FBI, no, they have. So if you'll write down F here, if you'll write down B here, and if you'll write down I here, this you must have done in class 11, some of you, those who had science, if you must have done here. If not, no problem. Here you only remember that which finger will give which direction. So just remember FBI and use it like a pistol. Okay. So what is this direction? F is for force. Okay. B is for magnetic field. There also B a cos theta. There also B was for magnetic field. So here B is for magnetic field only. Okay. So B is for magnetic field and I is for current. So it will give you the force, magnetic field and current. Okay. So that is your left hand rule, and it applies to the motors. Where does it apply? Applies to the motors. Okay. What is the right hand rule for the generators? So in this case, you will see that this one will give you the force, this will give the magnetic field. This is the induced current, but they have never asked a question on this ground. They have only stick to the left hand rule. So better you remember this one only. Same, if you will see, even if the question is changed, your answer will remain same, right? So it will not matter much. The only thing is you have to induce the current. So it will be called as the induced current in case of generator. All right. Now coming to what are the applications. This is the most important part which is asked in your examinations. That is the application part. So practical use, that is in the industrial magnetic separation of the ores can be done by this. Then MRI machines, in case of medical screening, they are using in case of the MRI machine. Electric bells, speakers, maglev trains, in case of trains they are using. So in all this case, what is being used? They are using the magnets, right? Now coming to galvanometer. Till now in electricity we had seen that if it is an ammeter, we are connecting it in series. If it is a voltmeter, we are connecting it in parallel. But now what is this galvanometer connection? You can see there is some high resistance which is there in series, and along with that you have connected a galvanometer as well, and this is going to give you the potential difference. So it is used to detect current and measure the potential difference. So galvanometer will do both of this task. You can use it to detect the current, and you can also measure the potential difference. Okay. And now finally coming to the important facts about the Earth's magnetism. Many a times they're asking you about this also, that earth magnetism is also there. Yes, earth itself works like a huge magnet. Okay, and earth's magnetism caused by which effect? Dynamo effect. What is this? Which one you will have to tick? You will have to tick the dynamo effect. Okay, what is this dynamo effect? There is the molten core motion which is there. If you will see the earth, then how it is, the inner core again becomes solid because of the high pressure and the high temperature, but the outer core is molten. Yes, the outer core is molten, and this molten core motion, this also known as the dynamo effect, that is the earth's magnetism. Okay, so earth itself, as you can see in this diagram, acts like a huge magnet. Okay, now coming to the field strength, we have seen by now many times that the maximum field strength is there at the poles. We have seen, right? And it is 0 at the center of the bar magnet. If you are considering here, do you see any field lines here? No, you are seeing the field lines in this towards the poles only. So what does it means? That it has the maximum at the poles and 0 at the center. Now for the navigation, the compass will always align in which direction? North-south direction. Often this north is your either put in a red color or sometimes put in white color. So you are able to identify that this side of this needle, compass needle, is the north direction, and it will always align in the north-south direction. And coming to path, a hypothetical free north pole would move along. So if you are suspending a magnet, okay, you can skip this part. If you are suspending a magnet freely, right, in that case they will show that, okay, this is the north and this is the south, and they will always align in which direction? In the north south direction. Quickly remembering the important units, okay, that they can ask. So remember the field strength. Okay, the field strength is, what is it? You can either use Tesla, or for the flux you can use Weber, and these are the important units that we are using. Okay, say number one, remember about the magnetic strength. It is denoted by FB. Remember, I. So I is for current, F is for force, and B is for magnetic field. And this magnetic field, it is given in Tesla. Then the magnetic flux, Weber, it is given in Weber. Solenoid, inside the solenoid there is the uniform field, whereas outside there is the non-uniform field. And you have learned about the right hand thumb rule and the left hand FBI rule, right? Now coming to which is scalar, which is vector. Magnetic field is in vector, since there is the direction for the magnetic strength, right? So magnetic strength is in vector, and magnetic field, we are just drawing the magnetic field line. So like that you can remember that it is scalar. Okay, now I think quickly the 10 minutes that we have, we can do some questions. I'll also like to show you one thing. These are the pages from the NCERT discussion that we have done. So you can go through them as well. See, there is about the lodestone we had discussed. One diagram I would like to show you here is this. That is why I kept this open, to show you this diagram that I was talking about. If you are actually placing the iron scrap, okay, if you are actually placing the iron scrap, if you are actually placing the iron needles in a bar magnet, then you will see this kind of an alignment. All the iron needles, they will come and stick to either the north pole or the south pole. This is the reality how it happens, right? So I think with this we can say that, okay, we understand that towards the center it is not there, but in the sides it is there. Merged. Okay, I will upload both of this. This one, this is like the picturization or very basic one. Okay, this has more details, like the units, etc. It is not there. It is very basic. Okay, but I will put this one also. This is the very simple one. Okay, very simple one. This is for again class 6 level NCERT. It is but many imagination, it becomes easy. That's why it was there. Okay, so I will upload this also. In that case, first you can go through this and then you can go through this. Okay, all right. Now coming to the questions, are we ready to solve in just for 10 minutes? We can solve some of the questions. Yes, just a second. Hello. 10 मिनट्स बाद करते हैं, ठीक है. Okay, now coming to this, just a second. Okay, so should we solve the questions? Okay, quickly let us try to solve this question. Magnetism is defined as a physical phenomena where certain materials exert. So certain materials will exert what? Only attractive force, only repulsive force. Attractive or repulsive force? What will be your answer? Yes, correct everyone. They can have both the attractive or the repulsive force. Okay, both can happen. Next question. The name of the person is more important, but in which year did Hans Ørsted observe that an electric current produces a magnetic field? Again, the name is more important. Who observed? Hence Ørsted observed. Okay, so in the year, okay, 1820. In the year 1820. All right. Next question. The name magnet is derived from an island in Greece which is called. Name magnet is derived from an island in Greece which is called. So initially just some warm-up based question, that is your, yes, it is for Magnesia. Okay. Next question. A natural magnet such as lodestone. What is it? Lodestone is an ore of which chemical compound? It is an ore of which chemical compound? So we had seen that it is Fe3O4 iron oxide, right? So yes, very good. So where is it? You have to find in the option Fe3O4. I think it is here only, Fe3O4. The first one only. Fe, it should be like this, Fe3O4. It just went running. No problem. Next, question number 5. Please look at question number 5. A bar magnet is considered what type of magnet because it retains its properties over time? A bar magnet is considered as, so if anybody is retaining its properties over time, we will call it as what? Will we call it temporary magnet if it is retaining? Only one wrong answer. Rest everybody has given the correct answer. If it is retaining over a long period of time, that means we will call it as a permanent magnet. Okay. If it is losing its property, if the cause is removed, say the electricity is removed, whatever cause was behind it, in that case it will be a temporary magnet. Here it is a permanent magnet. If the cause is electricity, that means it will be an electromagnet. So here it is permanent magnet. Look at question number 6. When a bar magnet is freely suspended, it points in which geographical direction? This was in the last slide also. Just a second. Here also, if you will say the freely suspended, it will always be in which direction? It will always be in which direction? Yes, it will always be in north-south direction. Correct. It will always be in north-south direction. I understood that. Next question is, according to the law of magnetic poles, what happens when two north poles are brought together? When two north poles are brought together, what happens? Like poles, they will always repel. Like poles will always repel. Outside of a magnet, the magnetic field lines extend from. Outside of a magnet, the magnetic field lines will extend from which direction? If it is outside of a magnet, it will be from North Pole to South Pole. Okay? It will be from North Pole to South Pole. Please note those who are writing that it is from South to North. I understand the reason behind this, why you are writing this. Outside of a magnet, they are asking. Outside of a magnet, the magnetic field lines will be from what? North Pole to South Pole. Okay. And if they would have asked inside of a magnet, then it would have been South Pole to North Pole. Just let us see here in one diagram. Okay. Okay, here also you can see North Pole to South Pole. Okay, so in this diagram also you can see North Pole to South Pole. It is being made. And here also you can see North Pole to South Pole. Okay, so this diagram was meant only for this, that outside it is north to south, outside it is north to south, and inside it is south to north. Okay, so inside it is south to north and outside it is north to south. So like that you can see this. All right. Which one? Outside of a magnet, the magnetic field lines extend from. This one? This is north to south. Okay? This will north to south. This one? This diagram? This, yes. Yes, the arrows, that's why while that one also, the arrows in the PDF, I will remove it because in case of the, that's why I did not say take that, because in case of the PDF, no, in case of the forming this diagram, sometimes they will mix in the, rarely it happens, but sometimes it happens. So that is why I will say correct it in case of that one before uploading the PDF. Okay. So outside a magnet, the magnetic field lines, it will extend from which one? From the North Pole. So here the answer will be North Pole. Okay. Okay. Coming to the next question. Coming to the next question. Question number 9. If a bar magnet is cut horizontally along its length, its magnetism becomes. If you will cut a bar magnet, horizontally, how you are cutting? You are cutting it along its length. Okay, you are cutting it horizontally along with its length. So its magnetism will be, what will happen to its magnetism? It will be doubled. No, you are cutting it into half. No, so it will be halved. Okay, this option did not come. It will be half. Okay, try one more question. What is the SI unit of magnetic field? What is the SI unit of magnetic field? The SI unit of magnetic field is, already we have studied, magnetic field. Okay, magnetic field. For magnetic field, if they are asking, what you will put? Yes, correct everyone. For magnetic field, you will put Tesla. Okay, so I think I will give you the rest of the PDF, entire PDF, and you can practice the rest of the question. Practice the other questions also. There are like 22 questions in this PDF. All right. 20 questions. One, I think, wait, let me check once. 25 questions are there in this PDF. Okay, 25 questions. This is the last one. 25 questions. You practice them, you will be able to solve all of them. All right. Okay, thank you everybody. I'm going to end this class here. I'll see you in the next class. All right. Bye-bye.